welcome to today's video. In this video, I will show you how to perform FE analysis on self-healing sheet memory alloy composite. This is taken from a request from a subscriber, so everything is from a research paper which was sent to me by the subscriber. The problem is not that complicated, but it requires steps to learn how to perform such an analysis, so I will go step by step. And the problem is we have a matrix and we have sheet memory alloy fibers into it, as you see here, and it can have a pre-notched sample or it can have a crack already inside the sample. So this is the initial configuration. Then in the experiment, what they do, they pull the sample in one direction and you see the crack starts to propagate, while your sheet memory alloy wires or fibers, they start to deform. And if you know the theory of sheet memory alloys can have elastic deformation in the austenitic phase, and then they start to transform into martensitic phase, and then they completely become martensite, and then everything is governed by that. Now if you unload the sample again, which is already transformed, then it again retransforms back to the austenitic phase. So this is martensitic phase, this area, and this is in between, and this is complete transformation back to austenitic phase. And same happens in the compression side as well. We worked on this for a long time ago, I would say almost 10 years ago, so my knowledge might not be that updated at this point from the research perspective. But what we did in that case was we expanded the shape memory effect, which is the pseudoelastic effect, to the elastic plastic part as well, because after a certain amount of deformation, with all the transformation has occurred, you will have plastic deformation in this material followed by failure due to the void growth, nucleation and growth. So that's what we did in our paper, and I will give you the reference at the end once I finish everything. So this is the problem here. We see we have two problems. We have a matrix which is an elastic plastic material, while we have shape memory alloy which has pseudoelastic response as shown here. And we need to define all these properties in the ABAQUS FEA software, and we need to see if we can simulate this crack behavior. So the problem is complicated, but it can be solved easily. We need to model these fibers. So we need to have like around 5 fibers in the matrix. We need to have a notched sample with elastic plastic properties, and then we have to define the crack propagation criteria along this line as shown here, because they found out that crack propagates in this direction. In the paper, when they simulated, they've used node release technique, so they already had nodes bonded here, and then as soon as you reach to the maximum stress, they start to release the nodes, and you will see this kind of crack propagation. So that's what they did, because at that time ABAQUS did not have that kind of robust way of propagating the cracks, or not, that was not common, I would say. So what else you can do is, other than using node release technique, you can use cohesive model here, because you know the direction of the crack, so you can use cohesive model and you can define those. Or nowadays people use XFEM, which is pretty robust in ABAQUS nowadays, so you can try that as well. First, show you how to model this fiber using this pseudoelastic response in ABAQUS in today's video. Next video will show you how to model the fracture if you have only matrix, and in the third we just integrate these two components together and do the actual simulation, but again using some fictitious set of parameters, and I don't want to really give you the whole solution. So let's move to ABAQUS and see how we can do the pseudoelastic response simulation in ABAQUS for a shape memory alloy only. Okay, let's jump into the details of how to model this. So I have already created a model. So what I did was to model the fiber. I have just created this single line. How you can do it is go to the create part option, select 2D deformable, and then wire. Then you can select a cable. In that case I think it was 6 millimeters long, so I'm just modeling that, and you see this is my length of that fiber. I'm calling it cable, sorry, but it's fiber. And then you go to the properties, and then you define the material properties. So for the case of shape memory alloys, I have to define the elastic properties. These are again given in that paper. For austenitic phase, which is the initial phase, and then for super elastic or pseudoelastic response, these are the parameters you have to define. Again, if you are confused about that, always good to look at ABAQUS documentation. So let's see if I can find something there. So this is there. I'll just go there and I will look at the keywords here, this one, and you see everything is defined here. M is the first term is the Young's modulus for the martensitic phase, then the Poisson's ratio of martensitic phase. So these are all here, which are these parameters here. Martensitic phase, Young's modulus, Poisson's ratio. Then transformation strain was the similar thing as, if you remember, in the PowerPoint which I showed you, it was a total strain for the transformation. So that's also given there, and you can read it from stress strain data, which was again given in the thing. Then you have stress at the transformation begins, then stress at which the transformation ends. These are those values. And again, I think you can, if you go back, you can really link everything with that. So you see, this is the curve I use here. So you see these are the start and end points for loading and unloading case, and then this is the total strain of transformation, and then this is under the compression side. So these values are coming from there. They were also provided, some of those were provided in that paper as well. So that's what I have used here. So this is start and for loading and unloading case. Then compression side, as you remember in that curve, reference temperature I'm using 0, but you can use whatever temperature was there. I think in that case they had 18.4, but I'm not doing any thermomechanical loading right now, so I'm just going to leave it like that. Then loading, this is again the change of stresses with respect to temperature. This is also given there, but at the moment it will not change anything because I'm not assigning any temperature values to that. Also, ABAQUS only uses a linear increase in temperature with respect to the linear increase in stresses with respect to temperature, and this is just 0 for this case because we are not having any shape setting effect. So again, all the data and everything is just, ABAQUS documentation is self-explanatory. Everything is explained here. You can look at that and you can definitely do everything what you really want to do. So this is the material properties I have defined. Then what you do is you create a section, you create a beam section. So what you do is you create a beam section here. In this case I'm using a truss element, so I create a truss section. So when I press continue, then I select this material properties and I press OK. You can also give the core cross section whatever is there, and in this case I have already defined, so I'm not going to create another one here. Then I assign this to this part, and I just do this and then I assign it to this part. So this is how I have done here. And next is to assembly module. I can instance the part here, which I already have done it. So this is here, just click on this and then bring it here. Okay, so that's already there. Now I go to the step and I create a general step. So I have 3 steps here because in their case it was loading, then unloading, and then heating, and then again relaxing. So I'm just leaving it like that for the time being, but I will explain those once we reach to the next step where we have the main matrix as well here. Okay, so this was just based on that. Just consider you have 1 step, right, for the time being. There is no interaction because it's just one component here, which is a fiber. So I leave it like that. Then I go to the loadings, and loading is very much the same as they had in their experiments. So I have no forces, but it was a displacement control test. So they had fixed because this is the one end of the matrix material, this is the other end of the matrix material. So I have fixed everything from one side, while on the other side I only let it move in the horizontal direction with the displacement of this, while I'm using an amplitude of amp1. And what is this amplitude? Again, you can create amplitude directly there, or you can create here from here. So you can create a amplitude button and you can give tabular, and then you can give the values here. So what I have defined here is at 0.0 it's 0, which is initial state. Then at half of the time step it will be 1, which is the maximum of the elongation, and then again it goes back to the 0. So I'm just trying to show you that my curve which was shown here can be somehow shown or predicted based on shape memory overlap properties of super elastic response in this case, because just trying to learn, this is the first step you always do. Rather than starting this complicated analysis, you first learn, okay, how do you model the shape memorialize, and how do you model the matrix material, how do you model the interface fracture in the matrix using node release technique, and then you combine everything together rather than start with the complex stuff. So everything is done incrementally. So this is what I have done here. So this goes like this and then comes back to 0 to capture that cyclic effect. Meshing, I only use 1 element here, so I just say the total length is 1. So if you see here, this is only 0.6, so well, I would say 6, the size. So I will have only one element here. Okay, and then I measure. So you can see I have only one truss element, and if I show you my truss element, so it is truss, and it should be okay. Right, so that's what I have done here, but this was part 2. So part 2 is already mesh, which is basically the main part. Part 3 is the fictitious part I created just now. Alright, now I go to the job and I just submit the job, which is this one. Matrix, I will come back in the next video, so don't confuse with that. Submit, and it's one element, truss element, it's linear element. You can even solve by hand if you have gone through my FEA course where I have showed you how to construct extension matrix for truss members. But why to do that if it's already there in the computer? Okay, so everything is going fine. You will see it finishes in quick time. My computer is getting slow because there are so many things going on right now. And then once it finishes, I go and results. So you can see, and this is step 1. So you see it starts to elongate and then it starts to contract back to the initial state. And that's what I have to plot, because step 2 and step 3 have nothing right now, because those are created for heating and cooling cycles, which I will explain in next video. Okay, now I go to the XY data manager, create field element label 1, save, and you will have the data now. And now you can combine them to get a stress strain response, because right now they are as a function of time, as you remember. So combine again, strains, then stresses, and then save, and I will just save it as a default name. Alright, so this is the data, and if I plot, so it looks like this. So you can see it has gone to that point, but it did never finish the whole transformation, so you just returned it back. So you have this loop, and that's why you have this thing. Alright, so we are able to capture. What you can do is, if you are not satisfied with the results, you can go back to the loading and you can basically increase the displacement to a larger value. Let's make it 0.5 now and see if I can finish the whole transformation thing and I can capture that cyclic effect which I want to see, right? So I'm just gonna go back to the job now, and then I will just submit again. It will not take more than 1 minute or so, so be patient, wait for it, and then you will get some fruit out of it. Right now I do this, and again I repeat the same exercise again for output post processing. I have created a lot of videos, so you can always find those videos to automate all this process which I'm repeating again and again. So create field output labels 1, save, create, operate on XY data, combine, save. Now I'll save it as XY data 2, so let's go with that. Then I will plot, and so you see it goes like this, transformation occurs, then it comes back like this, and so it's following some trend which we are expecting, and you can further expand it and you can see it will completely finishes, but I will stick to this. So this way I am able to predict or simulate the pseudoelastic or superelastic response. The next step is to model the matrix elastic plastic response and how to model the crack propagation in it. The failure analysis of the matrix using XFEM. We will have a matrix with an initial crack, and we will try to see how we can simulate the crack growth in that material, which is part of the SMA based composite failure analysis which we are performing. The loading and boundary conditions are given here. Okay, let's start doing the simulation thing. As you can see on the screen, I created a rectangular part. I will then include a crack somewhere here, as they have done in that paper which I showed in the previous video, and then I will associate that crack with this part, and then I will use XFEM to basically model the crack propagation. Alright, so first thing is how I created this parts. For those who are not familiar, you just press create part button, you select 2D shell, and then you select, in this case I just created a rectangular part which had a dimension of 6 millimeters in this direction, while I'm using around 5 millimeters in this, because I was not sure what was the dimension in this along this edge. So once you press this button and you press done, then you will have the part as you see here. Next thing is to create a crack. So again, I have created a small crack. I can show you what crack looks like. This is the crack, which is just a line, and it is very small. So what again you can do is you can use 2D deformable and then wire, and then you can select a small line and you can just do this, and that's your part 4. In that case I'm using part 2. Once you have created that, then you go to the next module, which is properties, and then you define material properties. So what I have done in this case is I have again taken the properties from that paper, and some properties I couldn't find there because I'm using a different type of model, so I took it similar properties. But again, the idea is not to use the right properties, just to show you the procedure. So I have used elastic constant as a function of temperature, which will be useful later on when we will be doing thermomechanical analysis at the end, which will be part 3 of this video, when this matrix will be integrated with the shape memory or fibers. Plastic part again is taken from the stress strain data, which was again given in that paper, and again it was a temperature dependent data, so that's what I'm using here. For the stress criteria, I use mechanical, and then I go to damage. In this case you have many different criteria available, like these ones. You can also use traction separation based laws. So I have used this maximum principal stress damage criteria. They use critical stress criteria using node release technique. I didn't go for that because XFEM, in my opinion, might do better job. Or you can use cohesive model as well, or you can use node release technique as they did, which was an older version of ABAQUS, and they didn't have XFEM, or even cohesive models were very new at that time. People were only using subroutines, UEL subroutines at that time. So I have used a value which was again the value which they use, 60 megapascals. For damage evolution part, this was not discussed there because they just release a node as soon as they reach to the stress value. So in this case we have to define this, so I'm using this value. Again, you can use a very small value as well. You might come across some convergence issues, and I will show you some of the ways how you can do it, or you can look at my damage model video, which is shown here, and where I have discussed all these convergence related issues and how to eliminate those. Alright, so these are the properties I have defined, and then I have nothing else to do. I'll just go to part 1, which was this part. I created a shell section, which is this one, by just pressing create shell homogeneous, and then if you look at this, so I selected this property there, solids homogeneous, sorry, because it's a plane strain case. And then you can see I have assigned it to this component here. That's pretty much it. So you see the color change shows that it was assigned to this. So this is how you assign the properties. Again, I have tutorials on how to assign different properties to different sections, so you can have a look at that. Then I came to the assembly module, and I bring both the parts together by selecting them here. Once I have brought them here, because the both parts are not aligned, so I have brought this part to this, aligned it at this position. So I just translate that component from that point to this point. Again, I have done a lot of tutorials on that, so I hope you guys know it. Otherwise you can look at those videos, that how to arrange parts in an assembly module. Then I go to the step module, and this is where you have to be careful. So first thing is I am using a static general step. You can just press create button and this window will come up. So I have turned on the automatic stabilization option, because as soon as your material will start to fail, you will come across negative stiffnesses, and your solver will struggle to converge. So that's one thing you have to do. Also, I've used a very large number of increments, so that if you go to a very large number increment due to the convergence problems, it can sustain those. Otherwise it will just stop after 100 or whatever number you have given it here. Also, minimum I have reduced it to 1 exponent minus 12, because sometimes it can take long. And also initially I start with this, and then I say that maximum use this. You can use 1 here as well if you want to do it, but it will keep on doing this. If you come across convergence during this time, what you can do is you can go to the general solver. Again, this requires very expert knowledge on these solvers and everything, so I would not suggest if you are new use it, but if you want, you can go to this and you can see it's giving you that warning as well that don't change anything at all. And here you can basically play around with line search, so you can enable line search in algorithm if you want. I have enabled it, but you can live without that as well. Also I have I have increased the number of iterations as well, so that because once it's in the downhill direction, when the stress is dissipating, reducing because of the damage, it should be able to survive. But if it doesn't, in this case it will not require, but I am just trying to show you, you can just disable it if you want. Alright, then for the output you need to ask for different types of output for XFEM. So I have asked for the status of the XFEM. I have asked for the element output for these normal elements as well, but not useful in this case. Also I have asked for this, which normally people ask, phi and PSIs, and also the damage initiation criteria, that where the damage, how much damage has been initiated. So this is what I have asked for. Other than that, I don't change anything here. Then I go to the interaction, right? And this is where you basically define the crack. So you had this crack, so now you go to special crack and then you say create. Okay, so in this case I have already done it. So when you press create button, it will ask you which geometry you have to select. So you have to select this geometry. You can see the region, and I have selected this region, that's why it's colored. Then you click on the crack location and then you select this crack, which I have already selected, like that, right? So once you have selected that, then rest is just fine. Other than that, you see there is nothing I have done here, nothing is there as well. So now ABAQUS knows that, okay, how to define or where is the crack. All right, and what else, if I'm not forgetting anything? Yeah, so then I have used the same boundary conditions that they did. So I have fixed it from the left hand side, and I'm pulling from this side with some displacement boundary conditions, and I am also fixing the bottom part. In their case, it was not clear to me if they had fixed it or not, but to be on the normal tension type tests, I believe it should have been fixed in the vertical direction. Otherwise you can just fix this corner as well if it was not. Alright, then mesh. Again, the meshing is normal plane strain element, so you just first do the seeding. Sorry, you have to select the part, seeding, and then I am using a seed of 0.1, and then I just use the element type, which is plane strain. You see plane strain standard element, which are linear and reduced integration. And what else I have to do? I just go to the job and then I submit the job. So once you submit the job, I have terminated it. As you can see, it will start to run and it will be finished in a quick time. So let's do it, see how it goes. So I started it. You can then monitor what's happening with your job, and you will see it goes up really fast, and you will see sometimes there are U's here. This means that point might be the place where your elements start to delete, or your stiffness starts to get negative in those elements which are failing. You see here a lot of them, and that will cause the time increment to go down in many cases. Then again, when it becomes stable, where your next element is loading, then it's fine. But as soon as it starts to fail, you will again see some issues with the convergence, and then again it caters for it as well. So solver is okay because we have used stabilization option, and I'm using line search as well. So it seems to be okay to me right now, and hopefully it will go through everything well. So I think by this time the failure has already occurred and it has already gone through the critical area, and that's why you see the time increment has reached to the maximum one. So let's go and see how the results look like. So if you look at this, so you see the crack has already propagated. So if I just go to the start, then you see the crack was initially here, and you will see stress concentration at this crack tip here. You see this is the crack tip, initial crack tip. And if I play the video now, so as the loading starts, your crack is there, everything, stress concentrations are there, and as soon as you reach to the 60 or something, the crack starts to propagate, and you can see it's propagating okay. In between it slows down because you have plastic behavior as well, so your crack tip might be blunting at that time. So that normally So you have a crack propagation, then arrest, and then propagation due to the ductile sort of damage. But you see, I mean, it's working fine, and your crack is propagating okay, and it finishes on time as well. So it doesn't take long. I don't have to run for the whole 1 second because it has already finished. The whole crack is propagated through the material at around 0.14 seconds. So I hope this makes sense. And next time when I come, I will integrate this component, this matrix, with the fibers which I built in the part 1 of the video, and then we will repeat the same exercise. How to do it, I think everything is the same. You just need to put the fibers here and then constrain it with the borders of this matrix as they did. But again, there are so many assumptions which are there, and we need to really carefully assume those. So as I said, it's not only the process you have to understand, but also the overall assumptions which are made and what are the justifications for that. That's the critical part. So approach is very important. So we will try to. In the first part, I showed you how to model a typical shape memory alloy, which shows the martensitic transformation, and then coming back to its initial state, that is the reverse transformation, we would say. In the second part, I explained to you how to model the matrix material using XFEM and see how the crack propagation in the matrix. And in today's video, I will show you how to integrate these shape memory alloy fibers with the matrix material, and then try to produce or show you how to simulate this kind of process, which was again sent to me by a subscriber via a paper. Paper was not that self-explanatory, and there were many things which were not explained there, so I had made some assumptions, and I will explain those assumptions as we go on. Again, if you haven't seen my previous videos, please first go through those part 1 and part 2 of the video, because I'm not going to explain everything what I have done for the fiber and the matrix before. I will just show you in this tutorial. So it is highly recommended that you look at that first. Thank you very much. Let's move into the real tutorial. Okay, let's start. So the first thing is the part I already showed you in the first part, how to draw the matrix material and then how to draw the fibers, and we already did the stress analysis on that in part 1 and part 2 for both the cases. So I have the parts. Properties are very much the same as I assigned before here. So you see I have the elastic plastic matrix and I have the shape memory alloy, and again the properties are, I have already discussed those in the previous video, so please have a look at that. It's very much what was there. Then I go to the assembly, and what I do is I bring the matrix material, and then I start to bring each of the fibers. So if I show you this model tree, then you will find out that I have 7 instances here, and each of these instances is the matrix, the fibers, and then I just adjust them. Once I bring them here, I just adjust them using translate option to align like this. Again, I haven't followed the same distances and same parameters as they have done in the paper, which was discussed in the first part, but I just used random distribution. So you see the gaps might not be as regular as it was in the paper. There are many things which are not clear in the paper, so I have not gone through that as well, and I have made assumptions, and I will go through them as we move on. So I have now assembled everything, but still they are separate. So ABAQUS doesn't know if these are all connected or not. In reality, these fibers should be somehow bonded. In the paper, they have given references and some assumptions they have made that these fibers are not bonded with the matrix, so they don't need to model any interaction between the two. But in reality, there should be an interaction, especially when it's contracting. Your fibers might start to kink or bend or buckle, and that there will be an interaction with the matrix, but that's not modeled here and also in that paper as well. But that's a key issue in this modeling, and one has to really justify why they haven't done that. Stepwise, what I have done here is I haven't modeled the whole thing again. I have modeled the loading part. So this is the first step where I load the sample. So I pull it from this direction as is given in the paper. I'm using the stabilization because I will have a crack propagation to avoid any convergence issues. I'm using a very large number of increments so that it doesn't stop if it reaches to a big number. And these are the minimum, initial, and maximum time increment sizes I have used. Other things are default, so I'm not changing anything. The second step is not necessary for you guys, but I normally do it after this kind of loading, especially once after I have done that. I want everything to stabilize, so I just stop everything at that point where it stopped in the last step, and I let it run without any changes, so that all the things and matrices are computed without any changes and everything is stabilized. So again, parameters are the same as before, and I'm not changing anything, so this is very much there, but this is not required in my opinion, but you can avoid that. And the third one is basically the unloading step, where I remove the displacement boundary conditional loading, and then it will start to relax as was done in the paper. Again, I'm using stabilization, and in this case what I have done is I have given a fixed time increment because it may take a long time because of the cracks and surface interactions. So I'm using a large number of increment, and I say that use increment size of 0.001 because there is not much of the loading or unloading, it's only unloading in this case. So I have assumed this value, which is more reasonable, but again you have to play around with this number to come up with a more accurate prediction. So, or again you can go with automatic as well if you want to. I just wanted to reduce my time for simulation. Alright, so this is for the step definition. If you want to have a thermal heating and then relaxation step, so then you can also create a new step, and you can just select, for example, from here couple temperature displacement analysis, and then you can define the predefined temperatures and see how temperature really changes the whole response. So I haven't done that as well. Again, I didn't have time for that, but if you require, just let me know. Now I go to the loading step, and in this case you can see I have no forces as was given in the paper, but in this case I have mostly displacement boundary conditions. So I have initially I fix this surface in x direction as I did in the first part for the matrix. In the second case I am fixing the bottom part of the matrix as I did in the first part again, and here I apply displacement boundary condition on a reference point. I have created an interaction between this reference point and this surface, so that I only have to apply displacement boundary condition on this. You can apply here as well, it's not a big deal. Still, ABAQUS doesn't know how these fibers are attached to the matrix, so we will define that in the next module, which is the interaction module. Then step 2, as I told you, nothing is there, so I just keep everything fixed, nothing is changing, and this means I'm just trying to stabilize the structure after crack growth and everything. And the last step is basically I just remove the x boundary condition and let it relax. So that's what I have done. There is no initial condition in this case, and this is just a temperature I have applied, which is the initial temperature. As I told you, if you apply a next temperature, because my material properties are with reference to 25 degrees, so I just defined that. But if you define a couple temperature analysis as a step 4, then you might have to apply a different boundary condition. In that case also, I think they have used the same procedure, but they didn't explain clearly what they did it. What you can do is you can increase the temperature here with in a temperature displacement analysis, and you can see the effect of temperature here as well, or you can apply the boundary condition, depends if there is conduction and convection going on in your material. So that's again not a big question which they haven't answered clearly in the paper. But I think if you assume that it's a very small sample and fusion it takes place really largely and everything is uniformly heated immediately, then you can just apply this predefined condition of temperature here directly, and I think that should be enough. But again, I leave it for you guys to decide. Mesh is the same. You see, this was a mesh for the fiber, and this is I use one element for this case, or for the fiber, sorry, and that was for matrix. All right, and yeah, interaction I didn't show you all. So interaction I missed, for example. So in this case I have an interaction which is the crack. So again, if you go back to part 1, I showed you how to define this crack thing. You have to go to special, if you remember, and you see I have defined a XFEM crack. You have to select the geometry, and then you have to select the crack. Where is the crack? So you have to pick this crack line, and again the whole process is explained in part 1, so have a look at that. And then so this interaction is basically about this crack, which we have already discussed. We have interaction type property, and this is just involved in the crack part. So now the important part is how to apply the boundary conditions. So I created a reference point. Again, if you remember, creating a reference point is you go to tools, create a reference point, and then click on any coordinate where you want to really create a reference point. And then what I do is I create, if you press create constraint, then I use this coupling option here, which will couple all the kinematic constraints or kinematics of the whole thing with a specific point. So that's what I do here. I select this surface, and then I select the control point, which is this reference point. So you see now everything on this surface is connected to this, and I'm only connecting in this case u1 because everything is fake, so I'm just moving in x direction so that it can still contract when I pull it, which is the case because of this surface is free. So this is again an assumption I have made, but yeah, you can decide if it's good enough for you or not. Second thing is how now to tell ABAQUS that these fibers are connected with this surface, right, or they are inside the material. So I use a tie constraint, which is the easiest way of doing it. So I select all these nodes of the fiber. You can do it by removing, you can create a node set by removing the matrix and create a node set for these fibers on this side, and then for the nodes at this side for the fibers, and then you select those as a master or slave, and then you select this surface of the matrix as one of the surfaces. Generally softer surface is assumed to be the slave surface, so again you can decide which one is softer in your case. And that's what I have done on the other side as well. So if you look at the other side, I go to click on this and then you see it gets red again. So I first created the node set for the fibers, and then I created the surface, and then basically I just defined them as in the interaction. So again, how to create it, you just go create constraint, select tie. When you select this continue, then it will ask you to select the surface or node region and then master or slave. So again, as I told you, the stiffer surface is generally recommended to be used as master surface, so I have done that this way. I'm going to cancel it because I already have these interactions here. So this way now we have told that this surface is associated with this end of the fibers, and this surface is associated with these ends of this end of the fibers here. And there is no interaction in between, as I told you, which is a critical issue, but in this case they avoid it. They ignored it, so, and they provide some just some references for that. All right, so that's what we have done here, and then I go there and then I run it. So you see I have run it and it's completed. So let's go to the result and see how it looks like. So you see my corrective was somewhere here. It grows in the first step. Let me play the animation. So you see it starts to grow, the fibers are pulled, and then in step 2 it relaxes, and then step 3 it starts to go back or relax because I have removed the boundary condition. So it was a quick simulation. As you see, you can play around with the things, like for example, if you want to see equivalent plastic strain in this material, so you can plot that. If you want to see the volume fraction of the martensite, so you can plot those. They are very much the same in all the fibers in this case at the end, but maybe it will change as you move around. So that's another thing. So you see now the distribution changes in the fibers because this volume fraction is changing for martensite. Also, so there are many things. So again, you can play around with that. You can see what is required for your own simulation, and you can do this way. So I hope this short video makes sense. I had been busy with many things, so it took me some time to prepare this, but in this short time I tried to explain to you. There are many assumptions and there are not many things which were not clear in that paper which was sent to me by the subscriber, but I had made some assumptions which I explained on the way. So again, you decide how to do it. Sometimes if you don't find information on the paper, it's better to email the corresponding authors and see if they can provide you more details. Generally people in academic world are helpful and they normally reply to you, so there is no harm in sending an email and ask them. So that's pretty much it. Enjoy your time. If you are interested in more reading, then we had done some work on porous shape memory alloy some time ago, almost 9-10 years ago, and this is a paper, so please have a look at that. If we developed a constitutive model where we extended the normal shape memory alloy model, constitutive model, to a porous shape memory alloy, because in porous shape memory alloy you have voids which start to grow and then coalesce, and your shape memory alloy can fail. So we worked on that. Also, as I told you, fiber matrix interaction is a very important problem. We have done some work in the past on that as well. So one of these papers is basically deals with that. In this case, it's not the shape memory alloys, but it gives you an idea that okay, how you can find out what is the bonding strength of a fiber with the matrix in your case. So again, you can do simple FE analysis by if you can get some fiber push out curves from some experiments or from literature. So all the best, and I will come back with some more interesting stuff in future. So bye for now.